Okay, let's start with something you might remember, maybe from a science class way back. Picture this, a simple prism, you shine white light through it, and bam, out comes a rainbow.
Right, that beautiful spread of colors.
Exactly. That simple act, splitting light, it's actually the seed for one of the most powerful scientific tools we have. A tool that lets us, well, quite literally, read the universe.
And that tool is spectroscopy. We're doing a deep dive into it today. It is the precise study of color, yes, but it goes way, way beyond just that visible rainbow. We're talking about the entire electromagnetic spectrum and sometimes even more.
It's the science of measuring and interpreting these spectra, these patterns of light or energy.
And our mission today really is to give you the shortcut, the essential knowledge to understand how spectroscopy works as this fundamental exploratory tool. You find it everywhere in science.
Everywhere. The main goal is getting information, right? About the structure, the properties of matter. Could be something tiny on an atomic scale or, something astronomically huge like a distant galaxy.
That's it. And the foundational idea, the really big concept that unlocked so much in physics and chemistry is this. Spectroscopy is the absolute key to understanding the atomic properties of all matter.
Because everything has a unique light signature.
Yeah.
Like a fingerprint.
Exactly, an atomic fingerprint. And spectroscopy is how we read it. It's the only way we know how.
Okay, let's dig into the history a bit, the origin story, because it connects classical optics, Newton, and his prism to the weirdness of quantum reality.
It really does. So yeah, you start with Isaac Newton, 1672. His famous paper on optics, he used that prism, showed that white sunlight isn't pure. It's actually a mix of all the colors.
And he coined the term spectrum for that rainbow he saw.
He did. But Newton saw a continuous spectrum, a smooth blend of colors, one flowing into the next. Things got much more interesting in the early 1800s.
How so?
Well, in 1802, you have William Hyde Wollaston. He built a better spectrometer, a more refined one. And when he looked closely at the sun's spectrum, he realized something crucial.
It wasn't smooth.
It wasn't smooth at all. There were gaps, missing patches, he called them, dark bands interrupting the rainbow.
Okay, so gaps in the light. And then came Fraunhofer.
Joseph von Fraunhofer, yeah. In 1815, a German physicist, he didn't just see the lines, he meticulously cataloged them, found about 600 specific, sharp, dark lines in the solar spectrum.
We still call them Fraunhofer lines, right? Absorption lines.
We do, absorption lines. And that was undeniable proof. Some kind of material, either in the sun's atmosphere or maybe even in Earth's atmosphere, was somehow absorbing very specific colors, very specific frequencies of light.
And that led to the core theory.
That's where it crystallized. The idea that every single element on the periodic table has its own unique, fixed spectral signature. It's defined by the exact frequencies, the exact colors of light it either absorbs or emits.
So if you see those specific lines, that signature pattern,
you know exactly what elements are present in the thing you're looking at. Whether it's a gas in a tube or a star billions of light years away, it's the atomic fingerprint. It's infallible.
that is just a staggering realization.
Yeah.
But okay, identifying elements is huge, but you mentioned quantum mechanics. How did these dark lines become so central to developing that whole field? Was it just about confirming Bohr's model of the atom?
It was more than just confirming it. It provided the critical experimental proof that forced a complete shift in how we understood reality. You see, before we had these precise measurements of spectral lines,
People thought electrons could just be anywhere around the nucleus, orbiting smoothly.
pretty much, yeah. They thought energy could be absorbed or emitted continuously, smoothly changing. But these lines, these discrete lines, meaning they appear only at very specific separate frequencies with gaps in between, they just couldn't be explained by that classical model.
So the gaps were the key.
The gaps, the discreteness, yes. It could only be explained by a really radical new idea. Electrons don't orbit smoothly. They exist in specific fixed energy states or shells, and they don't slide between them, they jump instantaneously.
The quantum leap.
The quantum leap. That idea that energy itself comes in discrete packets or quanta, and that electrons occupy these fixed orbits, that was the absolute birth of quantum mechanics. And spectroscopy, through models like the Rutherford-Bohr model explaining hydrogen's spectrum perfectly, provided the undeniable, irrefutable evidence for it.
Wow. So the absence of light, those dark Fraunhofer lines, fundamentally proved the existence of the quantum world. That's amazing.
It really is. It turned everything on its head.
Okay, so fast forward to today. When we talk spectroscopy now, it's way beyond just visible light and prisms, as you said. How do we organize all the different techniques? You mentioned it's based on the energy source.
Right, that's one major way we classify them, based on the type of energy we're using to poke the material, essentially. And the range is, well, it's genuinely mind-blowing.
So what are we talking about?
We start with the most familiar electromagnetic radiation. That covers the whole spectrum we know: radio waves, microwaves, infrared, the visible light we see, ultraviolet, X-rays, and even gamma rays. They're all just light, but with different wavelengths and energies.
That makes sense. We use different colors of light, broadly speaking. But you also mentioned going beyond light, using particles, or even sound. Why do we need those if light gives us the atomic fingerprint?
Because they tell us different things. Different kinds of energy interact with matter in different ways. So, yes, we use particles. Electrons, for instance, in electron spectroscopy. Neutrons, too.
Why neutrons? What do they show us?
Well, particles have wave-like properties, remember? Their kinetic energy gives them a specific de Broglie wavelength. And neutrons are fantastic because they interact really strongly with the nuclei of atoms, especially light elements like hydrogen.
Which X-rays often just pass right through.
Exactly. X-rays interact mostly with electrons. So if you want to study materials containing lots of hydrogen, like organic molecules, polymers, biological samples, water, neutron spectroscopy is incredibly powerful. It sees things other techniques miss.
Okay, interesting. And sound waves, acoustic spectroscopy.
Yes. Using radiated pressure wave sound. This isn't probing the electronic structure or the atoms directly in the same way. It's telling us about the bulk mechanical properties of the material. How stiff is it? How springy? How does it respond to physical stress? Things like that. Totally different information.
And you even mentioned gravitational waves.
On the absolutely largest scales, yes. Facilities like LIGO, the Laser Interferometer Gravitational Wave Observatory, detect ripples in space-time itself. And believe it or not, the patterns of those waves, their frequency, can be analyzed spectrally to understand the massive events that created them, like merging black holes. So yeah, a spectrum for almost everything.
Incredible. So we've got the energy source light, particles, sound. What's the other way we classify these techniques? You mentioned how the energy interacts with the material.
Right. The nature of that interaction is the second big classifier. The most basic distinction is between absorption and emission.
Okay, absorption is like the Fraunhofer lines, the material takes energy in.
Correct. Light goes in, some specific frequencies get absorbed by the atoms or molecules, and you look at what's missing in the light that comes out the other side. That's absorption spectroscopy. Classic technique.
And emission is the opposite. Material gives energy out.
Exactly. This can happen spontaneously, like the glow from a hot object, that's its thermal or black body spectrum, which tells you its temperature. Or we can induce emission. We excite the material, maybe with heat or electricity or other light, and then we measure the specific frequencies of light it emits as it relaxes back down. Think of the distinct color of a neon sign, or a sodium street lamp, or doing a flame test in chemistry. That's emission spectroscopy.
Makes sense. Then you mentioned scattering.
Yeah.
Where the radiation sort of bounces off. That sounds a bit different.
It is. Scattering is about how the radiation is deflected or reflected by the material. There's elastic scattering where the light or X-ray or whatever bounces off without losing any energy. It just changes direction.
What's that used for?
That's the fundamental principle behind crystallography. You shoot high-energy X-rays, or sometimes neutrons or electrons, at a crystal. The regular, repeating arrangement of atoms in the crystal lattice scatters the X-rays in very specific directions, creating a diffraction pattern. Analyzing that pattern lets you map out the precise 3D structure of the atoms in the crystal. Hugely important.
Okay. And then there's inelastic scattering.
Right, and this is where it gets really interesting for probing energy levels. In inelastic scattering, there's an exchange of energy between the radiation and the material. The scattered light comes out with a slightly different wavelength, meaning a different energy than it went in with.
Why does that happen?
Because the light has either given some energy to the material, maybe causing a molecule to vibrate, or it has picked up some energy from the material. Techniques like Raman spectroscopy and Compton scattering rely on this. Raman, for example, is fantastic for identifying molecules based on their vibrational modes.
Got it. Absorption, emission, elastic scattering, inelastic scattering. Is there one more main type? You mentioned resonance earlier.
Yes, resonance techniques. These are often incredibly powerful and give very high-resolution information. The most famous one is probably nuclear magnetic resonance, or NMR.
NMR. I've heard that, especially related to MRI in hospitals.
Exactly. MRI is basically NMR imaging of the water in your body. The core idea of resonance spectroscopy is tuning into a perfect frequency match. In NMR, you put your sample in a very strong magnetic field. This causes the nuclei of certain atoms, like hydrogen protons, which act like tiny magnets themselves, to align with the field, but they also wobble or precess at a specific frequency.
Like tiny spinning tops.
Sort of, yes. Then you hit the sample with radio waves. If the frequency of your radio waves exactly matches the precession frequency of those nuclei, the resonant frequency of the nuclei absorb that energy and flip their alignment. When they flip back, they emit a radio signal that we can detect.
So it's like striking a bell. Only the right frequency makes it ring loudly.
That's a great analogy, precisely. And the crucial thing is that this resonant frequency is incredibly sensitive to the chemical environment around the nucleus. What other atoms is it bonded to? What are its neighbors? So by measuring these precise frequencies, NMR allows us to map out the detailed structure and connectivity of molecules. It's indispensable in chemistry and biochemistry.
Okay, that clarifies the how. So we have all these methods using different energies, looking at absorption, emission, scattering, resonance. Let's switch focus to the what. What kinds of matter are we actually analyzing with this giant toolbox? Starting small, with individual atoms.
Yep. If you're studying individual atoms, maybe in a gas, you're looking at those sharp atomic spectral lines we talked about earlier. Those lines correspond to electrons jumping between the outer energy shells, the electron orbitals.
And this is how elements were discovered.
Absolutely. Back in the 1860s, Robert Bunsen, yes, of Bunsen-Burner fame, and Gustav Kirchhoff used a spectroscope to look at the light emitted when different substances were heated in a flame. They realized certain elements produced unique sets of bright lines, their emission spectra. And by observing new, previously unknown lines, they actually discovered new elements, like cesium and rubidium. That's the absolute core of elemental identification.
Amazing. But what happens when atoms join up to form molecules? Things get more complicated, but we also get new information, right?
Way more complicated, but yes, much richer information. Molecules aren't just about electron transitions anymore. Because you have multiple atoms bonded together, the molecule as a whole can rotate, and the bonds between the atoms can vibrate like springs, stretching and bending.
And these motions also involve specific energy levels.
They do. Molecules can only rotate at certain specific speeds, and their bonds can only vibrate at certain specific frequencies. These also correspond to discrete energy levels. So molecular spectra are much more complex than atomic spectra, often showing broad bands made up of many closely spaced lines.
So how do we study these motions?
We use different types of spectroscopy. Rotational spectroscopy, which looks at the energy needed to make a molecule spin faster, typically uses microwave radiation. Vibrational spectroscopy, which probes the stretching and bending of bonds, mainly uses infrared light. Raman spectroscopy, which we mentioned under inelastic scattering, is also excellent for studying vibrations.
And studying these molecular spectra was important for other technologies.
Hugely important. In fact, detailed research into molecular energy levels, particularly using microwave spectroscopy, was absolutely critical for the invention of the maser microwave amplification by stimulated emission of radiation, and that, in turn, led directly to the development of the laser. So, understanding molecular spectra had massive technological spin-offs.
Wow. Okay. From atoms to molecules. What about when you get huge numbers of atoms or molecules packed together in solids, like crystals and other extended materials? Does spectroscopy still work?
It does, but it looks different again. In a solid, especially a highly ordered crystal, you have trillions upon trillions of atoms interacting strongly with each other. This causes the individual atomic or molecular energy levels to broaden out and merge into continuous bands of a loud energy.
So you lose those sharp lines.
Often, yes. The density of available energy states becomes very high. So absorption or emission spectra of solids tend to be much broader, sometimes looking more like that continuous black body spectrum we mentioned, related more to temperature than specific electronic transitions.
But crystals have that ordered structure. Doesn't that help?
Ah, yes. While the absorption emission might be broad, that perfectly ordered lattice structure is exactly what makes elastic scattering techniques like X-ray diffraction or neutron diffraction so incredibly powerful for solids. The regular spacing of the atoms acts like a diffraction grating for X-rays or neutrons, producing those patterns that let us map the crystal structure precisely.
So different techniques for different forms of matter. We've done atoms, molecules, solids. Can we go even deeper? To the nuclei themselves.
We absolutely can. The nucleus of an atom also has its own set of discrete, quantized energy states, but these energy levels are much, much further apart than the electron energy levels.
Meaning you need higher energy radiation to probe them.
Exactly. Transitions between nuclear energy states typically involve absorbing or emitting gamma rays, which are the most energetic form of electromagnetic radiation. So, gamma ray spectroscopy is used to study nuclear structure, often important in nuclear physics, astrophysics, and certain types of materials analysis.
And NMR fits in here too, right? Nuclear magnetic resonance.
Yes, but NMR is looking at something slightly different. It's not usually about transitions between the main nuclear energy levels, like gamma spectroscopy. It's about those much smaller energy differences created when we put the nuclei in a strong magnetic field, the energy splitting of the nuclear spin states.
Ah, the tiny magnets aligning or opposing the field.
Precisely. That energy splitting typically corresponds to radio wave frequencies. So NMR uses radio waves to probe the immediate environment around specific types of nuclei within a molecule or material. It tells us about chemical structure, molecular dynamics, and it's the basis for MRI, giving us those incredibly detailed images of soft tissues in the body.
Okay, this toolbox is immense. We started this whole deep dive thinking about Newton and a prism on a desk. Let's zoom way out now. Where is all this fundamental science actually being used today in the real world?
Oh, it's absolutely everywhere. It's hard to overstate its importance. Let's start big. Astronomy.
Okay, telescopes.
Pretty much every major research telescope in the world, whether on the ground or in space like Hubble or JWST, has a spectrograph attached. Or often, several spectrographs optimized for different wavelengths. They are completely essential.
Why so essential? What are they telling astronomers?
So much. First, chemical composition. By identifying those atomic fingerprints, the absorption or emission lines in the light from a star, a galaxy, a gas cloud, we can tell exactly what elements are present and even in what abundances. We can also determine temperature and density from the details of the spectra.
So we know what stars are made of, even light years away.
Exactly. But maybe even more crucially, spectroscopy tells us about motion, velocity,
How does that work?
the Doppler effect.
Yeah.
Just like the pitch of an ambulance siren changes, whether it's coming towards you or moving away, the wavelength of light changes too. If an object is moving away from us, its spectral lines get shifted towards longer wavelengths, towards the red end of the spectrum. We call it redshift.
And if it's moving towards us?
Blue shift. The lines shift to shorter, bluer wavelengths. By precisely measuring the amount of this shift for a distant star or galaxy, using the relativistic Doppler effect formula, we can calculate exactly how fast it's moving towards or away from us.
And that's how we know the universe is expanding.
That is fundamentally how Edwin Hubble discovered it in the 1920s, and it's how we continue to map the expansion and the large-scale structure of the cosmos. Measuring redshifts is absolutely foundational to modern cosmology.
Mind-blowing. The ultimate long-distance application. But you said it's everywhere. What about closer to home? Medicine and biochemistry.
Huge applications there, too. Biomedical spectroscopy is a massive field. It's used for analyzing tissues, often non-invasively. For example, pulse oximeters that clip on your finger. They use absorption spectroscopy with red and infrared light to measure oxygen levels in your blood.
Ah, I never realized that was spectroscopy.
Yep. It's used in medical imaging techniques beyond MRI, too. And for monitoring things in real time, like checking the dissolved oxygen content in water for environmental science, or even analyzing the gases a patient is breathing in and out during surgery in hospitals.
Practical and potentially life-saving. What about industrial uses? Manufacturing, quality control?
Definitely. It's vital for non-destructive testing. You need to check the composition of a batch of metal alloy, or verify the purity of a chemical, or monitor the curing process of a composite material. Spectroscopy lets you do that without cutting the sample open or destroying it. X-ray fluorescence, XRF, is a very common technique for rapid elemental analysis in industry, for instance. It's also used for process monitoring, keeping an eye on chemical reactions in real time in industrial plants.
Okay, astronomy, medicine, industry.
Yeah.
Any really surprising or niche applications?
Well, one that caught my eye in the research was using spectroscopy for in ovo sexing.
In ovo, sexing. What on earth is that?
It means determining the sex of a chicken embryo while it's still inside the egg before it hatches.
Yeah.
Apparently, they can shine light through the eggshell and analyze the subtle spectral differences likely related to hormones or other biochemical markers to tell if the embryo is male or female.
That's technically fascinating. Why is that needed?
It turns out it's driven by major ethical concerns and regulations. In commercial egg production, male chicks of egg-laying breeds are typically culled shortly after hatching because they don't lay eggs and aren't suitable for meat production. This practice is highly controversial.
Ah, I see. So this technology allows them to identify and discard the male eggs before they hatch.
Exactly. It avoids the culling of live chicks. Countries like Germany and France actually mandated bans on chick culling starting around 2022, which rapidly accelerated the development and adoption of these in ovo sexing technologies, many of which rely on spectroscopy.
Wow, so fundamental physics, light analysis, Fraunhofer lines, directly leading to a solution for a major animal welfare issue in agriculture. That's quite a leap.
It really shows the incredible reach of the science, doesn't it? From probing quantum mechanics to influencing agricultural practices based on societal ethics.
And is this tech super high-end, or is spectroscopy becoming more accessible?
That's another great point. While the cutting-edge research instruments are obviously complex and expensive, the basic principles of spectroscopy are actually becoming incredibly accessible now.
You mean like for schools or hobbyists?
Yeah.
The sources mention DIY spectroscopy.
Exactly. There's a whole maker movement around it. People are building their own functional spectrometers using really simple, readily available components. Like you can use a piece of a CD or DVD as a diffraction grating to split the light.
Seriously?
A CD?
Yeah. The closely spaced tracks act just like the lines on a proper grating. Combine that with a simple slit, maybe a lens, and then use your smartphone camera as the detector. There are even designs for 3D printed bodies to hold it all together.
And apps to analyze the results.
Right, smartphone apps and open source software can capture the image from the camera, analyze the spectrum, calibrate it, and display the intensity graph. It really democratizes the whole process.
Now, obviously, a DIY smartphone spectroscope isn't going to compete with the Hubble Space Telescope spectrograph. Of course not. The resolution, the sensitivity, the wavelength range, they're orders of magnitude different. But that's not the point. The point is it provides invaluable hands-on educational experiences. You can actually see the discrete emission lines from a neon lamp or the absorption lines in sunlight yourself. It drives curiosity and citizen science initiatives. You can build a tool in your garage that demonstrates the fundamental principles that let us analyze stars.
That really brings it full circle, doesn't it? From Newton's prism through discovering elements in quantum mechanics to analyzing galaxies, checking blood oxygen, sexing eggs, and now building your own in the garage.
It does. We've seen how taking some form of radiation, light, particles, even sound, and just carefully measuring how it interacts with matter gives us this incredibly deep, fundamental understanding of pretty much everything.
The sheer precision is what gets me. That a tiny shift in wavelength or a specific missing color can tell you so much. Identify an atom, map a protein, determine the speed of a galaxy, or even the sex of an unhatched chick. It's almost unbelievable.
It truly is. And that precision, as we saw, was what allowed us to discover elements in the first place and provided the bedrock, the experimental proof for quantum mechanics itself. And the field is never static. It's constantly being refined. Think about databases like the NIST Atomic Spectra database.
Run by the U.S. National Institute of Standards and Technology.
That's the one. They are continually measuring and remeasuring these atomic fingerprints with ever-increasing accuracy and making that data publicly available. Precision is always improving.
So given the spectroscopy has already cracked open so many secrets and enabled entire new fields of science, what's the final thought you want to leave our listeners mulling over?
It's this. Considering the incredible precision we already have, and the fact it's constantly improving, and knowing how it's revealed unexpected things like quantum jumps and enabled applications we couldn't have dreamed of centuries ago, the real question is, what fundamental property of matter, something currently hidden from us, maybe something we don't even have a concept for yet, will the next generation of spectroscopy reveal? What new secret is waiting in the light?